For quite a while, people have envisioned what life might be like in other universes. On account of the James Webb Space Telescope, the most impressive telescope in existence, that question can at long last be investigated. By observing the nearest star system to us, Proxima Centauri, which is just 4 light-years away, researchers have seen a few particular irregularities from one of the planets in the system, Proxima b. These abnormalities, called fake lights, have astounded the best minds in mainstream science. But what do these lights suggest? Could they point to the presence of intelligent life on the planet? Join us as we explore the James Webb Space Telescope's alarming revelation of city lights that could change everything. The only life that we are currently aware of is on Earth. Since the dawn of civilization, people have questioned whether there is life elsewhere in the universe. To pursue such an interstellar hunt, American astronomers Jill Tarter and Thomas Pearson launched the Search for Extraterrestrial Intelligence (SETI) project in 1984. The nonprofit's goal was to gather spaceborne radio transmissions, as radio waves can travel farther and are consequently more likely to be detected by the 42 radio telescopes that make up the extraordinary Allen Telescope Array in the California Sierra Nevada mountains. However, in the past 30 years, no conclusive extraterrestrial signal has been found. Following that, the James Webb Space Telescope's successful launch bolstered the mission to inspect a range of unseen planets circling distant stars. As the largest telescope in the world, drifting around 1 million miles from Earth and equipped with astonishingly sensitive detectors, it has the potential to reveal critical discoveries. 20 years ago, there were no known planets outside our solar system. However, since then, more than 4,000 exoplanets have been found orbiting different stars. According to NASA, the universe may contain trillions of exoplanets. The early indications of something happening on distant planets could be seen in extraterrestrial vegetation. The Galileo spacecraft, on its course to Jupiter, turned its gear back toward Earth and found a distinct sign of plant life, identifying the vegetation's red edge biosignature, a blend of red and infrared lights reflected by plants. For example, a planet like Earth, covered in a jungle, should have a solid and easily discernible V-shaped signal. The JWST will measure the V of distant, Earth-like planets in the habitable zone around stars, which could provide significant indications of what is happening on the surface of these exoplanets. When sunlight crosses a planet's star, the JWST might be able to identify it as it enters the atmosphere. Missing frequencies would then be found through spectroscopy, as particles and atoms in the atmosphere absorb specific frequencies, creating a characteristic fingerprint that the JWST can recognize. This method might be used to determine the composition of the atmosphere and whether life is possible. Life could exist on Earth-sized planets with atmospheres like our own, composed of a mixture of oxygen, nitrogen, and carbon dioxide. By searching for components that aren't typically present, one might be able to identify intelligent life. For instance, chlorofluorocarbons, CFCs, gases produced for use in refrigeration and cleaning products, would likely be recognizable to outsiders observing Earth's atmosphere from afar. If the JWST finds CFCs in planetary atmospheres, that would send an obvious signal of civilization. However, life on exoplanets might not resemble life on Earth in any way. Sometimes even natural living things like extremophiles, species that can survive in conditions where other living things would die, can appear to be alien. This group of organisms, primarily microbes, can endure extreme conditions such as heat up to 250 degrees Fahrenheit or strong acids with pH levels under 3. Since planets like Earth are more likely to support life than those with extreme temperatures or acidic conditions, it may be wise to start with Earth-like candidates. Prime candidates could have temperatures that allow liquid water to exist on their surfaces and orbit a stable star. Our Sun is classified as a yellow G-type star. These stars are rarer and generally have shorter lifespans. However, in our universe, the probability of studying planets orbiting red dwarf stars, which are more common and have lower luminosities and temperatures than the Sun, is higher. This extended time frame allows for the development of life and evolution to produce complex organisms. Around 40 light-years from Earth, the TRAPPIST-1 planetary system will be the subject of the JWST's first mission. It revolves around a quiet red dwarf star with 7 Earth-sized rocky planets. 3 of these rocky planets, situated in the so-called habitable zone, could have liquid water on their surfaces. Despite its smaller and colder mass compared to our Sun, the TRAPPIST-1 star emits light similar to that of Earth. Due to the close orbit of its planets, the most obvious opportunity for us to see city lights outside the solar system is Proxima Centauri. A red dwarf star that is 4.25 light-years from the Sun. Proxima is multiple times fainter than the Sun, so a planet would need to be much closer to it than Earth is to the Sun to support life based on liquid water. In August 2016, cosmologists found a planet with 1.3 Earth masses in this habitable zone, like a Goldilocks zone where the light intensity is perfect to melt water. Proxima B orbits Proxima Centauri, but it is possible that Proxima B is an airless, dormant planet, given that it orbits its red dwarf star at a distance of just 4.6 million miles. This close orbit exposes it to strong solar winds that can completely strip away its atmosphere. However, Proxima B receives enough sunlight for temperatures and liquid water like those on Earth due to its proximity to the star. Proxima B is believed to be tidally locked, consistently showing the same side to the star, much like the Moon does in relation to Earth. Proxima Centauri is about 18% the mass of the Sun and emits significantly less light than one would expect for a planet so close to its star, only 5% of the Sun's brightness. It might seem like a scorching ash, but liquid water could exist on Proxima B as long as the planet has an atmosphere to retain heat. Since the total energy reaching it from the Sun is just 65% of what Earth gets, the planet isn't particularly hospitable to life. It is most likely tidally locked, meaning it always faces the same side toward the star, resulting in permanent day and long-lasting night with extreme temperature variations. The planet also receives 100 times the amount of high-energy radiation that Earth does, including X-rays and ultraviolet light due to its proximity to Proxima Centauri. Proxima B is also bombarded with high-energy particles during stellar flares. Unless it has a protective magnetic field like Earth's, the conditions for life may not be favorable. Still, practical conditions might make Proxima B a more attractive world. Unfortunately, models suggest that the atmosphere of tidally locked planets might be vulnerable to rapid collapse due to the freezing out of volatile gases on the night side. Our planet's atmosphere can be replenished by volcanic activity, and for planets with strong magnetic fields, this atmosphere is less likely to escape. Since we know nothing about Proxima B's volcanic activity or magnetic field strength, we can't even speculate whether the planet has an atmosphere. However, since an atmosphere implies the presence of oceans, and both together suggest the presence of life, we are eager to know whether Proxima B has a complex ecosystem. It could have solar panel channels covering the day side to produce energy to light and warm the night side, which would otherwise be excessively cold and dark for comfortable habitation. The discovery of Proxima B has sparked a race to determine whether it crosses its star's face as seen from Earth. These transits would allow researchers to determine the planet's size and mass, enabling them to estimate its density and confirm the planet's rocky composition, providing information on the materials used to form those rocks. During a transit, starlight could reveal the composition of the planet by passing through its atmosphere. However, the probability that the orbit will be in the right alignment for researchers to observe a transit is only 1.5%. The star's tendency to flare complicates matters. Astronomer David Kipping of Columbia University states that the star is unstable, as stellar flares cause a rocky planet to absorb sunlight and re-emit it as infrared light. However, rocky planets produce a particular type of infrared radiation from stars like Proxima Centauri. Furthermore, the James Webb Space Telescope was specifically designed to focus on infrared light. Proxima B's infrared intensity signature is the key to identifying the planet's atmosphere. Additionally, the infrared part of the spectrum has strong advantages over Hubble's replacement, which might allow the JWST to observe city lights on Proxima's night side, even if they are as faint as those currently used on Earth. The JWST could detect artificial lighting as long as it is confined to a frequency band much smaller than the star's light. Proxima B's day side might be heavily covered with solar panels reflecting starlight. As Proxima B orbits its star, it faces a constant cycle of day and night, with cool night lows following daytime highs. The temperature difference between day and night, however, depends on whether the planet is entirely composed of bare rock. If there isn't an atmosphere, Proxima B's day side and night side temperatures will vary more, since the day side will emit all the energy it receives from Proxima Centauri as a black body. We can compute the exact amount of black body radiation that should be present. The night side, on the other hand, would resemble a frozen wasteland. If the temperature contrast between day and night is less pronounced, we can infer the presence of an atmosphere. Conveniently, it will only take the JWST 11.2 Earth days to measure the infrared radiation from Proxima B's two faces after it has completed its orbit around the star. If Proxima B has an atmosphere, the next step will be to investigate its composition. The presence of gases like oxygen, water vapor, and methane could specifically indicate the existence of habitable conditions, if not actual living organisms. However, to achieve this, we must successfully capture starlight as it reflects off or passes through the planet's atmosphere, which is a very challenging task. The JWST can closely examine a few of the nearest potentially habitable worlds, but it was not built to search explicitly for extraterrestrial life. Moreover, it is limited to tracking changes in the atmospheric concentrations of methane, carbon dioxide, and water vapor. The JWST cannot identify the presence of free oxygen, which is the strongest evidence of something living, even if some combinations of these gases might suggest life. One of the planned ground-based observatories that will be able to conduct a detailed atmospheric analysis is the Extremely Large Telescope, expected to begin operations in the 2020s. Ozone might be among the substances that the JWST is capable of detecting. Until those telescopes are operational, the JWST may provide information that we can consider for 10 years into the future. Furthermore, more advanced space telescopes may employ cutting-edge techniques to disguise the blinding brightness of a planet's host star and uncover starlight reflected back from the planet. After starlight is blocked, focusing on light glistening off a planet becomes much simpler. Sadly, most of the gases produced by terrestrial life can also be generated by non-biological processes. For example, methane is a gas produced by both cows and volcanoes, and sunlight can convert water molecules into oxygen and hydrogen through photosynthesis. While searching for alien life, cosmologists are certain to encounter some false positives. Consequently, space scientists need a thorough understanding of a planet's conditions to assess whether its geological or atmospheric processes might resemble a biomarker, helping to rule out false positives. The next wave of planetary analysis may yield the compelling evidence needed to establish the reality of life. The James Webb Space Telescope's fundamental data gives us a glimpse of the significant changes to come. If there is life elsewhere in the universe, it addresses one of science's most pressing questions. Is it possible that life is abundant throughout the universe? Or could it be that we are utterly alone, confined to a single planet in deep space? In either case, profound philosophical or existential changes among humans will likely be essential for the inevitable resolution of this quest. The search for extraterrestrial life has captivated humanity for decades, inspiring countless stories and theories. As we advance technologically, our understanding of the universe expands, revealing more possibilities for life beyond Earth. The use of space telescopes like the James Webb not only enhances our ability to detect distant planets, but also allows for detailed analysis of their atmospheres, helping scientists identify potential biosignatures. Moreover, the investigation of exoplanets fosters collaboration among global scientists and international organizations in space research, promoting knowledge sharing and resource pooling, thus increasing the chances of significant discoveries. These collaborative efforts also enhance public interest and engagement in space exploration, as discoveries are often shared with a broad audience, igniting curiosity and imagination. Ultimately, the philosophical implications of finding life elsewhere provoke deep reflections on our existence. With the discovery of extraterrestrial civilizations, our understanding of life's purpose would change. Such questions challenge us to reevaluate our role in the universe and our relationship with our home planet. As we continue to refine our technologies and methods for exploring the stars, each new discovery brings us closer to answering the age-old question: are we alone in the universe? The journey ahead is filled with potential, driving the pursuit of knowledge and understanding beyond our earthly limits, as we venture further into the study of exoplanets and potential extraterrestrial life. The tools at our disposal are becoming increasingly sophisticated. The James Webb Space Telescope, JWST, is just the beginning of a new era in space exploration. With its incredible infrared capabilities, it has the potential to reveal much more about distant worlds than ever before. While current methods focus on detecting biosignatures and atmospheric compositions, future missions and technological advancements could push our understanding even further. Upcoming telescopes, like the Extremely Large Telescope, ELT, will be able to capture more detailed data on the surfaces of distant planets, offering more precise images and spectra to look for signs of life or habitability. Additionally, future space telescopes could employ advanced techniques, such as direct imaging of exoplanets by blocking the overwhelming light of their parent stars, allowing us to detect even the faintest of signals, perhaps those emitted by intelligent civilizations. The search for extraterrestrial life also has the potential to reshape humanity's understanding of its place in the universe. If we find evidence of life beyond Earth, it would challenge our very notions of existence and open up philosophical debates about the nature of life itself. How would such a discovery impact our cultural, religious, and scientific paradigms? Would it alter the way we view our responsibilities toward preserving life on Earth and nurturing our own biosphere? On the other hand, if we find that Earth is unique in its ability to harbor life, it could provoke deeper existential questions about the meaning of life and our role as stewards of the only known habitable planet. In the broader context, the pursuit of finding life beyond Earth also drives technological innovation. Many of the tools and techniques developed for space exploration have practical applications here on Earth, leading to advances in fields such as medicine, material science, and environmental monitoring. As scientists push the boundaries of what is possible in the search for life, they also enhance our ability to address the challenges we face in preserving life on Earth. Ultimately, the quest for extraterrestrial life is not only a search for answers to profound questions about the universe, but also a journey that may illuminate the path to solving some of the most pressing challenges here at home.